Great. So we are happy to have Anthony Bonato from Ryerson University. I know Anthony from many seminars. He's sort of very involved in graph searching and processes and graphs and whatnot. So he's going to discuss today interesting process of graph burning and answer something, giving us closer to answering a conjecture. So Anthony, take it away. Thank you.
Thanks, Carrie, and thanks everybody for the invitation. I'm really happy to be here. So I am going to talk about graph burning, and I'm going to tell you what that is in just a second. So I'm at, we're calling it now X University, I put with an asterisk. The university is in the process of renaming, acknowledging that sort of history of the namesake, which was Ryerson, Egerton Ryerson, who was very heavily involved in the architect, I guess you'd say, of the residential school system in Canada, which you probably have heard of. So the university shall be renamed, and we will hear about that later in the year, I think. So I'm going to tell you about burning.
Anthony, if I may interrupt, I think your iPad is being recorded, so the recording doesn't have your face and talking on it.
Okay.
Is that okay?
That's fine with me, yeah.
Okay.
But you can see me, right?
Yes, we can see you.
Okay, but just it won't be recorded, I understand. So what is burning? It's a graph process, and every vertex is in one of two states, either burning or not. So if a vertex is burning, say like I have X in this figure, in the next time step, the next round, all of its adjacent vertices will catch fire, will burn. So there's a series of discrete time steps, starting at the first time step, which you can call round 0, and then the process continues over time. Now, if you're familiar with graph percolation, this is somewhat analogous to that. The difference between this and percolation, however, is that you introduce new sources of fire over time. So you call a source a vertex that you choose to burn, and in every round, as long as you can do it, you're going to choose a new vertex that's going to be a source. So it's a new source of fire. So what you'd like to do then, of course, is like consider a sort of an optimization situation. You're trying to minimize the number of rounds it takes to burn the entire graph. Of course, you could sort of burn every vertex, but you usually need a lot less than that. But the minimum number of rounds to burn each vertex is the burning number, and that's well defined. So we're going to call that B of G. And it's a graph parameter. You can study it, try and find bounds, algorithms, understand its properties. So some examples. If you're familiar with, as Carrie mentioned, graph searching or vertex pursuit games, you may have heard or you've been a talk about graph burning. If not, let's do an example just to illustrate. So let's start with a path with 4 vertices for a simple example. So say I use red just to emphasize that we're burning things. All right, so say you use that vertex as the first source, and I'll label that 1. Okay, so it's going to then spread, the fire is going to spread to the neighbors in the next time step, which will be 2. And you're going to choose a vertex to burn, which I'm going to circle there. And so that's 2. So in 2 rounds, you burned every single vertex. So you see that the burning number in this situation is 2. So what happens with the 6th cycle? Well, it's also burning number 2. Let's see why. So if you burn that vertex first, spreads to these, and you can choose this vertex. And then in the next time step, you're going to burn 3. And notice that there's nothing left to choose. So you could, if you want, for redundancy, choose that vertex which is already burning, but it's sort of like overkill. But regardless, 3 steps is enough. So the burning number is at most 3, and you can argue that this graph is burning number 3. It can't be burned in 1 or 2 rounds. So the burning number in this situation is 3 for this graph. So what we get when we're burning is we have this sequence of sources, right? The first source, second, third, and so on. So what you get is a sequence, a burning sequence. And the optimal length burning sequence, we're calling the optimal burning sequence, is length the burning number G. Of course, you can see just from these simple examples that the burning sequence is not unique, right? You don't have to have it be just one thing, up to symmetries and so on. You can find other burning sequences, but again, the length of an optimal burning sequence is unique, and that's the burning number. So I have chat open, and of course, feel free to chime in anytime if you have questions for me. So a little bit of background about graph burning. It's a relatively new process. So it came about in Ellen Rochenben's doctoral thesis, which she finished in 2016. She was a PhD student of mine and Jeanette Jansen. And there was a proceedings paper in 2014 where sort of the early ideas were sort of stated. And around that time, 2016, the paper How to Burn a Graph appeared in Internet Math. And that really contains the core of graph burning, definitions, and lots of different results about it. Now, I've been talking about graph burning as a process, and you can think of it as a process. In some cases, it makes sense to do that. Another way, and something we're going to see of relevance today, is you can think of burning really as a kind of partition problem, okay? So burning, having a burning sequence, say x1, x2 up to xk, those vertices in order. So x1 is the first source, x2 the second source, and so on, is equivalent to this set equation, all right? So this one here, the union of these closed neighbor sets being the vertex set, and also the sources, the second line, the sources being sufficiently spaced out, because you don't want to do sort of overburning. So the idea there is that you have these balls in this sort of metric space sense. So you're thinking of your graph as metric space with the usual graph distance. The balls around these, you have the first source, which is going to burn, like say k-1 vertices in a sphere around it, and then k-2 the second, and so on, all the way to the very last one, which will burn maybe like one vertex. That's sort of the goal. You're trying to cover the graph in this sense, pack it or cover it, however you want to look at it, with these balls. Of course, these kind of covering problems have been around for a long time, but this is a very specific one, right? Looking at the balls of very specific radii decreasing in this order. And there's a question here. Was there an application in mind for this concept apart from arson? Yeah, like it's pretty awful, like burning, because like we're going to burn trees, which doesn't sound very nice, right? Where the motivation came from was social networks. So we're looking for a process on social networks, like a contagion, like obviously relevant in the age of COVID, where it's spreading, right? Which is not a new idea, but new sources of contagion appear over time. And one of the key motivations was looking at memes, which, like I was talking to a student about this who was like, a second year undergrad. And I said, do you know what a meme is? He said, I'm under 25. Of course I know what a meme is, right? But with memes, like you can imagine on Instagram or something, someone puts something up, right? And that spreads to their followers, and so on. But then other people will start posting that sort of randomly. Or you can think of like a contagion like COVID. Okay, you have a population where, a contagion like COVID is spreading, but then maybe people are coming in on different flights and, bringing in new contamination. So that's the motivation. That's how we're thinking of it. How to ruin your friends' circles most efficiently. Yeah, so I mean, that's the motivation, but it's also just like a pure graph theoretic problem. And one fun thing about it, like I mentioned with trees, so trees play a very important role in graph burning. In fact, cycles don't really seem to have much influence at all. If you have a graph, the burning number of that graph is the burning number of some spanning tree. So in fact, what you get is that the burning number is the minimum of all the burning numbers of the spanning trees of G. Now, this is a really useful approach. We're going to use it today, but it's not universally used. Like there are some instances with different kinds of graph families where you want to burn and you're not using a spanning tree. You're using structural properties of the graph. But it really depends on your sort of theorem or things you're after. So in that paper in 2016, there was also this result that the burning number of an isometric subtree is at most the burning number of G. So just to recall what I mean here by isometric, I mean that distances within the subtree are the same as the distances outside. Okay, so it doesn't hold in general for all subtrees. Like you can look at something like this. Let me see here. Let me get rid of that. I think 5 works. Yeah, I think this is a nice example to look at. So here, the situation is the burning number is 2, right? This is your source, and then all of these become on fire in the next step. But of course, if I take away that vertex, I look at the tree, just the path, and the burning number is 3. So, it's not true in general for trees, but for, this is not an isometric subtree, but in general, it holds for isometric subtrees. But in general, we don't have the inequality. So some quick inequalities that we can derive. First off, by looking at the longest path, which is going to be isometric, you get a lower bound, which is the diameter of G plus 1, all square rooted. And I'll explain where that comes from a little bit more as I talk about burning paths. And also, you can take a central vertex in your graph or your tree and just burn it and just have that as the only source in a sense, and just let the fire run from that. And that'll take radius of G plus 1 steps. And these bounds are actually tight. So many things have been done now. So there are probably, at least 24 papers that have appeared about burning since the initial work was done. Grids, of course, really interesting kinds of graphs. Cartesian grids where, you have cells which look like 4 cycles. These have been studied quite a bit, and there are various results in papers. And strong grids where you have, the cells now being like K4s. Binomial random graphs people have looked at, and other graph families like generalized Pearson graphs and so on. So I didn't cite all these, but if you go to my survey paper from 2021, there's sort of a pretty exhaustive lit review of all the different results there. So you can take a look at that. So what else can we say? I mean, I guess the next obvious direction to look at would be complexity. Algorithmic questions. So if I gave you a graph of order n and a fixed integer k, or some integer k greater than or equal to 2, you can ask if the Burning number is at most k. So this is the decision problem that you can consider. Not surprisingly, because it's a kind of partition / coloring type problem, you can imagine this is NP complete, which it is. But interestingly, perhaps, if you look at very specific kinds of trees, so spider graphs, these are trees which have exactly 1 vertex of degree at least 3. So you have a situation like this. Okay, so you have paths of various lengths attached to a root vertex. And what I said is not quite correct. It also include paths themselves, but regardless. So you just attach, paths to a given vertex, you get a spider, and the problem is NP complete for that. And I have an instance of a spider here, and there is an optimal burning sequence. And also it's kind of surprising, maybe not surprising when you look at the proofs, but surprising initially that for path forests, so these are forests where every component's a tree. So just like a disjoint union of, forests where every component is a path. These are just disjoint union of paths. That's what I'm trying to say. So for this situation, again, it's NP complete. And also for caterpillars. So caterpillars have a central path, and then every vertex is a degree 1 attached to that path. So something that looks like this, right? You can have many different vertices of degree 1 attached to a single vertex, but there's just this path. Everything is essentially distance 1 from that central path. So 2 groups of authors proved this for caterpillars, but also caterpillars of max degree 3. So like very, very sort of specialized classes of trees, it is NP complete. And we know some things about approximation algorithms, so looking at competitive ratios. So things like path forest, there's a 3/2 approximation algorithm. I did that with Thomas Lidbetter. And with Shahin Kamali, we have a 2 approximation algorithm for trees. Okay, so there's a fair bit that's known about the complexity, still some interesting questions. Probably the central question, the question that comes up over and over, and one that we don't have a resolution for, is what we call the Burning Number Conjecture, or the BNC. So what does this say? Okay, so we want to avoid the situation of path forest. We're going to talk about connected graphs, right? So if G is a connected graph, the Burning number is at most the ceiling of the square root of n, where n here is the order, the number of vertices. Okay, so this is the conjecture. We first stated it in that proceedings paper. And I'll try and motivate a little bit why we think it's true and what we know. We don't know how to solve it, but we know some partial results. Let's take a look at P9. So the conjecture says the Burning number is at most 3, and why would that be? You don't burn the center, which is maybe like tempting to do in this case. What you're going to do first is burn this 3rd vertex. So I'll label that 1 just to keep track of it. And that will spread to its neighbors, and then burn this vertex as the 2nd source, the 7th one. Then that's going to spread in time step 3. and you're going to choose that as your source. So that's how you burn P9, all right? And that is an optimal burning sequence. The result, actually, which maybe some of you thought of, but it takes just a moment's reflection. Actually, it's not completely on the surface. You need to think a little bit that the burning number of a path is realizing this upper bound. It's the ceiling of squared event. So where does this come from? So I'm going to just give you a sketch of a proof of how it works for the lower bound. So assume that your burning process lasts k rounds. K is some positive integer that we don't know yet. Now, if you look at what happens with sources, so here I have a figure with source at x. I mean, think about what the balls look like. They're just intervals, right? And if I choose the ith source, to the right of it, you're going to burn k minus I vertices, and same at the left, right? Just these closed neighbor sets around x. So you're going to have 2 times k minus I plus 1 vertices burned, right? And you're doing that for each of the sources, the first source, which burns like the most, then the second source, and so on down to the last vertex. So what you get is a sum of odd integers here, right? And it's all odd integers up to k. So that's k squared, and it has to be at least n. Solving the inequality gives a lower bound. So this is how it works. And for the upper bound, I mean, I won't do it here. Really, it's an exercise. You just give an explicit burning sequence, which really amounts to, again, partitioning the path into these intervals. So how do you burn trees? How do you burn trees? Because we know trees are sort of play a central role in the theory of burning. Well, take a look at this tree, which I've drawn sort of in a rooted way at A. But it doesn't have to be rooted in general. But think of this sort of depth first search type algorithm. So let's use this color. Maybe I'm going to use yellow. Why not? Just for emphasis. So I'm going to move along to B and then to F. But in this, okay, let's move along to B and then to F. But what I'm going to do is I'm going to go back to B and then back up to A. Then explore to C, G, go back to C, H, up to C, back to I, C, go up to A, go to D, just explore in this depth first search fashion, and you see that you're going to get a walk, which will cover every single vertex in the graph. And this is like sometimes called like an Eulerian tour, and the number of vertices, so if you have n vertices, basically you're using at most 2n vertices in your walk. So unfold that to like a long path, with repetition, and just take the burning number of that. We know the burning number of a path of order 2n would be at most root n's, so like you get this upper bound. So that's like a quick upper bound that you can get on the burning number of any tree just by using that sort of an idea. Now that's not what the conjecture is saying though. We want this multiplicative term times n to be 1. So this doesn't give the conjecture, but I'm just sort of explaining like in this sort of more heuristic fashion, like how you would do it and get an upper bound. Okay, so since you can't resolve the question in general, it's natural to consider families of graphs. So like I mentioned, spiders seem to be an important family, and there are examples of spiders, infinite families of spiders, which realize this root n bound. But with Thomas Leadbetter, he and I proved that you always have the BNC holding. So the BNC holds for spider graphs, which, with spiders, you can take away the head, like for example, this vertex labeled 1 there, and you get a path forest. So I mentioned this 3/2 approximation algorithm. Essentially, the idea there for this proof is to find bounds on the burning number of path forests. I mean, there's some obvious bounds in terms of the number of components and so on, but you can get more subtle bounds. And then you use that with an induction, and you can prove the result for spiders. Again, not like you'd think that would be easy, but it's not exactly, like a 1-page proof. It takes some development to actually prove it for spiders. And Hiller et al. Proved the result for caterpillars, which I mentioned, right? So the BNC holds for caterpillars. So again, central path and vertices distance 1 away. You may be familiar with the family of lobsters, right? Like all these people always laugh at graph theorists, all these funny names of things, right? Lobsters, so you have the central path and every vertex is distance at most 2 away. So again, there you can prove that BNC holds. So the best known bound that was around for some time was due to Lincoln Liu and Max Land, who proved the following, that the Burning number is the ceiling -3 plus the root of 24n plus 33 over 4. And that just reduces down to essentially, root of 3/2 n plus an additive constant. So this was the best that we could do up until what I'm going to tell you today. And an interesting result, not super long to prove actually, but it's very interesting, that if you have minimum degree at least 23, then the BNC holds. So as long as your minimum degree is not too small, you have it. Of course, this doesn't include trees and many other families of graphs, so it's fairly restrictive. But it does suggest, and I'll talk more about this later, some relationship between the burning number and the min degree. It's always interesting to find connections with these sort of parameters and, very common existing statistics in graphs like the min degree. And so there does seem to be some sort of relationship there, and I'll talk about that near the end. So with Shaheen, we found a proof that the Burning number is at most square root of 4n over 3 plus an additive constant. To be precise, this is the bound that we have, and I'm going to explain how the proof works in just a second. So this does beat our 3/2. So like I said, the Liu-Land result is root 3n over 2. And what we were able to show is root 4n over 3. So our constant's a little bit better. Okay, and the ideas, I'm going to explain how the proof works. The overarching idea is essentially an algorithmic one. Using this idea of thinking of burning as a partition problem. So we're going to take, first off, we're just going to focus on the spanning tree. Okay, so without loss of generality, right? It's not an issue to do that. So you take your graph, your connected graph, and form a spanning tree and prove the result for that. So with T now, what we're going to do is we're going to cover T by some subtrees. And the subtrees are very specific in terms of their radius and their order, and I'll explain that. So we're going to partition our tree into K trees. K is like our Burning number that we're going to find. TK minus 1, TK minus 2 up to T0. The radius of the TJs is at most J. And we're thinking of TJ, right? J is just your index between K minus 1 and 0. TJ is burned by the K minus J source. Okay, so initially at 0, you have like the Kth source, then the K minus 1 source, and so on. So this idea, this algorithm, you keep extracting these trees. The radius is not too large, R star, which is the radius at most J. And the order of your graph, you're going to choose to be R star plus the floor of J over 2 minus 3. And this is chosen, so J is decremented, right? Going down from K minus 1 to 0. Okay, so this is the overarching scheme, the goal, right? We have our tree and we want to partition it into these subtrees with very specific radius and specific order. Now I'm going to use a lemma. I'm not going to prove it. It's probably folklore. It's not difficult to see that if beta is a real number in 0, 1, and R is a distinct set of non-negative integers, indexed this way, so R1 up to Rj in increasing order, you can find an R star sandwiched between these two bounds. So the lower bound 1 minus beta j and upper bound Rj minus beta j plus 3. Okay, so just a technical lemma. We use this a couple times, and yeah. So we root a tree, let R be 0 up to K minus 1, and we'll let J iterate from K minus 1 to 0. So what are we going to do? I need to find an R star in my list of radii and a vertex P with the following properties. This is going to be our new goal. Okay, so the radius of this subtree shouldn't be too large. It should be at most R star. And the order of the subtree should be large enough. It should be at least R star plus the floor of J over 2 minus 3. Okay, so you're thinking of your tree, you're thinking you're going to find a vertex P with these two properties. So 1 and 2, very, very important. We're going to come back to these. We have to do, unfortunately, a little bit of case analysis, but not too much to sort of establish this for all trees. Okay, so what do we do? If we can do this, we then update. So we then take away R star and TP. And we just keep on going. And we keep on going as long as we can. And this will give us our partition. All right, so what are we going to do with our tree? Well, I'll label U as a deepest vertex. So, you know, our tree is rooted, right? I didn't label the root, but you're thinking of that. It's a rooted tree, and you look at a vertex as far away from the root as you can. You're going to call that U, okay, the vertex U. Now, you're going to define V to be an ancestor closer to the root, right, of U, with a property that its distance from V to U is just Rj. Okay, so some cases. The first case, the order of TV, the subtree, is large. Okay, so what do we do in this situation? If it's a large order, that likely means that our condition 2, remember our 2 conditions, the first one is the radius not too large, the second one is the order is large enough. In this situation, the order is large, so we should get 2 for free, which we will. So what I'm going to do is I'm going to let P here, in this case, be V, and R star be Rj. So immediately, because, you know, the way you've defined it, right, V is distance Rj from U, the radius of TP in this case is at most R star, so 1 follows. So this is an easier case. The order, which is the order of TV, is at least Rj plus J over 2. So if you subtract 3, of course, that inequality holds. So 2 also holds. So 1 and 2, remember, those were the things we want in each case. 1 and 2 hold in this situation. So for case 1, fairly straightforward, not much to do. For case 2, it is more involved. So let me explain how this works. So in this case, you're thinking of the order not being too large. And what that means is the order of TV being at most Rj plus J over 2. So we'll just set the order of TV to be Rj plus Cj. And C here is just some constant less than 1/2, okay? So I've just labeled it this way. C is just a constant I choose to make this happen. So again, you're thinking of this path from U to V, and its distance Rj. So the path has Rj plus 1 vertices. So what that means is that outside that path, you have less than Cj vertices, right? Of TV not on the path. So outside the path, you have Cj vertices. We're going to come back and use this fact a little bit later. Okay, so I haven't used the lemma. So let's use the lemma with beta equal to 1/2 minus C. You'll find an R star sandwiched between these values, and I'll call these 2 inequalities star. So just some subcases. First, if R star is large, it's bigger than Rj minus J over 2. In that case, what I'll do is I'll again let P equal to V. So we did that in case 1, right? So let's compute the diameter of TP. Well, it's Rj plus Cj at most like the order, right? And by hypothesis, right, by our assumption with R star, that's at most R star plus J over 2 plus Cj, right? Just rearranging the inequality in our hypothesis. And by star now, using that inequality, I believe the left-hand side, you're going to get that's at most 2 R star. So diameter is at most 2 R star, so the radius is at most R star, and so case 1 follows. And the order, well, the order we know is Rj plus Cj. And again, this time using the other part of the inequality of star, right? We're going to, sorry, I mean this one. So using the right-hand side of star, we're going to use that and derive that this is at least R star plus 1/2 minus Cj minus 3 plus Cj. Simplifying, I get R star plus J minus 2 over 3, and 2 also follows for this case. So subcase is not too bad, and that's when the radius is, or the R star is large. Case 2.2, this one has some more subtleties. So R star in this case is at most Rj minus J over 2. Okay, so when I introduce a little bit more terminology, I'm going to let H be a vertex, which is distance R star plus J over 2 from U. Right, so you're thinking of this path from U to V. P is going to be that vertex, which is that distance away, that H distance away. And since H is at most Rj, it's bona fide in TV, so you're good. Now, the order of TP is certainly the order of that path, right? So we have this, and so 2 follows. So that part is is very, very easy, right? It's just immediate in this subcase that the order is large enough. Where the subtlety comes is from looking at the radius. So how does that work? Well, we're going to claim that the diameter of TP is at most 2r star. So how are we going to prove this? Well, okay, so you look at maybe this picture, this will help. You're thinking of that path from U to V. You have this P, which is distance h away. And you're just going to choose X and Y in that subtree, TP, which have maximum distance. If we get a bound on this, we get a bound of 2r star, we're done, because then that's going to show the diameter is upper bounded by that term. So invoke the triangle inequality. Not much else you can do, right? So thinking of the distance from X to Y, I could think of, see if it shows up, maybe I'll do it in orange. You know, you go to A, it doesn't really show up because this is overlay, but you get the idea. You're going from X to A and then down to Y. So you get this inequality, right? By the triangle inequality. U is the deepest node, so I can replace this by DUA. No problem there. And you're on a path, right, in a tree. So DUA plus distance AB, this is like distance from U to B. So I can replace these two terms by this. I actually have quality. Now H, remember, is the distance from U to P. So DUB is at most H, okay? No big deal there. And this is where we use this fact I mentioned about CJ. So there are less than CJ vertices in TV not on the path. So that DBY is going to be at most CJ. All right. Definition of H is just R star plus J over 2. And then we invoke our star and we get that this term is at most 2R star. So what did I show? What's the big picture here? I took a pair of vertices, distance, the distance between X and Y being maximum in my subtree TP. And I've shown that the distance is at most 2R star. So the diameter is at most 2R star, so the radius is most 2R star, so the case follows. Okay, so that really establishes 1 and 2 in all the cases. We've covered all the possible cases. So those do all hold for general trees. So what are we going to do now? Now it's bookkeeping. So we've extracted these subtrees. We want to get a sense of their order. Well, we know what the order is. We know like they're lower bounded by this R star plus J over 2 minus 3. So sum up all the orders of the TPs. That's going to be at least the sum of all the R stars. And then I have a sum J equals 0 to K minus 1 of floor of J minus 2 over 3. Okay, so with capital R, I just have the vertices or the integers from 1 to K minus 1. So I'm just summing those up, which we know how to estimate those, of course. And then just a little bit of bookkeeping with the floors. So, it could be that J is odd. So J over 2 is not an integer. So you decrement a little. Like there are about half the terms that become about a half smaller. So just use that fact. And this is, bounding above this term, which is J over 2 minus K over 4. And for this part, I just summed it up from 0 to K minus 1. So I get 3K. So put that all together, I get this quadratic 3K squared minus 6K over 4. And I'll call that function f of K. All right, so that's the sum of all the orders. That's the lower bound for it, right? F of K. And as long as n is at most f of K, you can solve the quadratic to get K at least this root 12n plus 64 plus 8 over 3. So as long as you can do that, as long as you have this inequality on K, the algorithm terminates with this partition of T into subtrees with a given radii. So there you go. That's how you prove it. So again, the overarching idea is, really you're looking at the cases of like the order being large and the order small and the radius of this R star being large and small and breaking this in cases. So there is some case analysis, but it's not too bad. Okay, but some really recent stuff, we can actually do better. So the story is, there's a little bit of the story. So Shahin and I posted on RPath. This was back in 2021, near the end of the year. And I got an email from Martha Bonamy saying that actually we have the same result, very similar. So we talked about it, sort of compared notes, and decided to all submit together instead of competing, right? That's sort of silly. So what we can do in our joint effort is this. So we have the Burning number of G being at most the same multiplicative constant. Okay, so we can't prove that. It's 4/3 n. So that's the state of the art, right? We can't beat 4/3. If anyone can beat 4/3, then, well, you know, I guess our paper is kind of irrelevant. But for now, this is like today, this is the best known bound. And we do have a better additive constant too than what I presented. This is +1, which is tighter. Okay, and there's more. By looking at spanning trees with a certain number of leaves, there are various results you can invoke. There's one I think of West, one of Griggs. So if the minimum degree, I mentioned the relevance of the min degree. If the min degree is at least 3, the Burning number is at most the ceiling of square root of n plus 2. So very, very close to the Burning number when you have the minimum degree at least 3. So that includes a lot more graphs. Still doesn't include trees, of course, but you know, you're getting closer. You're getting closer and closer to the Burning number here. And in fact, if the minimum degree is at least 4 and n is sufficiently large, in this case 325, then what you've got is the full-on conjecture. So it feels like we're getting a lot closer. Obviously, you know, we want the delta to go all the way down to 1. I mean, that's really in the realm of trying to find these bounds. But the techniques that we have, the upper bounds that we have, so this new proof with the +1 is pretty analogous, using the same kind of ideas, essentially a partition algorithm into subtrees of given radii. We couldn't push that further to further reduce the 4/3 n. So we don't know. I mean, at this stage, the conjecture remains open. It's possible our bound is tight. I don't believe that, but it's possible. There's a little more we can say, though, which kind of suggests that the Burning number is true. And let me tell you about that. So by the way, this is a paper, Bastide et al., like a number of co-authors. It just appeared on the archives. So this is available publicly, just as of like Monday. Okay, so let's define growth. So what is a growth? It's basically generalizing the central path in caterpillars. You have a central path and you have every vertex, just have a path, not central, just a path, and every vertex is distance the most k from that path. Okay, that's what we mean by growth. So every graph, every tree has a growth, right? For a given k. Caterpillars are growth 1. That's one simple way of saying it. They're trees with growth 1. Lobsters are growth 2. So growth is one way of thinking about how to generalize those results for caterpillars and lobsters, which are, you know, they're nice, but they're kind of some sense ad hoc, like just very specific families. So growth is what we think kind of a natural extension. So what we can do is the following. And actually the bulk of our paper is spent on this, that if you're growth k, then the BNC is asymptotically true, essentially. That the Burning number of T is at most root n plus 20k squared. So notice the multiplicative constant in front of n is 1, which is great. So we do have this error, but essentially it amounts to showing, without getting into details, it amounts to showing that for a given k, there are only finitely many cases to check. So in a sense, if I give you a k, we have a bound, and you can just check those cases. Now that sounds easy, but you could have to check, you know, trillions of cases depending on k. The number of cases will increase as a function of k, and so it's not kind of a meaningful approach to the BNC. But for small k, you know, if you're a programmer, maybe you analyze like trees up to order, you know, 300 or whatever, you can verify. So yeah, so this gives like another interesting direction perhaps to look at in terms of growth. Shin mentioned recently, I don't know a lot about it, there's this notion of tree length, like, you know, about tree width, there's a notion of tree length. So this notion of growth is sort of related to that. Anyway, so that's pretty much everything I want to say. I know I'm a little bit early, but my main goal was really just to sort of focus in on that proof and this new result, and also to give you sort of a survey, and I'm happy to take questions. Before we do that, I do want to plug a book. So this also is recent news. So I have another book coming out for the AMS. Super excited about this. It's called An Invitation to Pursuit of Asian Games and Graph Theory. So I wrote a book in 2011 with Richard Nowakowski on cops and robbers, which many of you are very familiar with. Much has been done since then. So burning didn't exist at that time. And there's also this new pursuit evasion game called localization, which is really cool. And of course, there was this work before, like Torrance Parsons and Seymour and others had done all this work on graph searching, like proper, where you're trying to clean edges and so on. So I decided, like, okay, I'm going to try and write a book which will, summarize all that. And I did, and it's been accepted to AMS. It should come out a little bit later this year. Don't have a specific date, but you'll be hearing more from me. And if you want to follow me on Twitter, you can do that. And I think that's everything. So thanks so much for your attention, and I'm happy to answer questions.
Hey, thank you, Anthony. Want to take questions with recorded, or do we want to stop the recording and do questions? I'm not sure how you want to do that, Sandra.
We can stop recording. So
okay, great. So we'll stop the recording.